Hi everyone, this is Ms. Sanchez, one of your AP Geo teachers, and today this lecture is going to be talking about contemporary geospatial technologies. The growth and advancement of three interrelated geospatial technologies, global positioning systems, remote sensing, and geographic information systems, has completely revolutionized geography and increased a geographer's ability to collect, analyze, and visually represent some forms of geographic data. Global positioning systems, GPS, rely upon a system of 24 orbiting satellites, earthbound tracking stations that control the satellites, and portable receivers that determine the exact location geographically based on the time delay signals received from three or more satellites. Technically, they determine the location from an inference based on time required for several signals to travel from the satellite to the Earth and back. Remote sensing allows the collection of vast amounts of geographic data as well, while geographic information systems, GIS, can integrate GPS, remote sensing, and other forms of spatial data. Google Earth and interactive mapping and navigation websites such as MapQuest are everyday uses of contemporary geographic research technologies. Remote sensing. Remote sensing is a relatively new term, but the process that describes detecting the nature of an object and the content of area from a distance is more than 150 years old. Soon after the development of a camera, photographs were being taken from balloons and kites. In early 20th century, fixed-wing aircraft provided a platform for the camera and photographer by using, by 1930s, aerial photography from planned positions and routes permitted reliable data gathering for large and small area mapping purposes. Even today, high and low altitude aerial photography with return film remains a widely used remote sensing technique. Standard photographic film detects reflected energy within the visible portion of the electromagnetic spectrum. It can be supplemented by special sensitized infrared film that has proved particularly useful for the recording of vegetation and hydrographic features, including thermal, and widely used for various aspects of water features such as ocean currents and water pollution, and because it can be employed during nighttime hours for military surveillance and radar mapping. For more than 30 years, spacecraft, with or without crews, have supplemented the airplane as a vehicle for imaging Earth's features. Among the advantages of satellites are the speed of coverage and the fact that the views of large regions can be obtained. In addition, they are equipped to record and report back to Earth's digitized information from multiple parts of the electromagnetic spectrum, including some that are outside the range of human eyesight. Satellites enable us to map the invisible, including the atmospheric and the weather conditions, in addition to providing images and applications for agriculture and forest inventory, land use classification, identification of geological structures and mineral deposits, and very much more. The different sensors of the American Landsat satellite first launched in 1972 and are capable of resolving objects between 15 and 60 meters. Even sharper images are yielded by the French SPOT satellite launched in 1986. Its sensors can show objects more than 10 meters. Satellite imagery is relayed by electronic signals receiving stations where the computers convert them into photo-like images, then use as scientific research and mapping programs.
Hi everyone, this is Mr. Longer, other AP Human Geography teacher. Today I will be talking about GIS, which stands for Geographic Information System. Increasingly, digital computers, mapping software, and computer-based display units and printers are employed in the design and production of maps and the development of databases used in map production. In computer-assisted cartography, the content of standard maps, reference, and thematic is digitized and stored in computers. The use of computers and printers in map production permits increases in the speed, flexibility, and accuracy of many steps in the map-making process, but in no way reduces the obligation of the map maker to employ sound judgment in the design of the map or the communication of its content. GIS extend to the use of digitized data and computer manipulation to investigate and display spatial information of all types. A GIS is both an integrated software package for handling, processing, and analyzing geographical data and a computer database in which every item of the information is tied to a precise geographic location. In the section above that we just discussed and introduced geographic features, we discussed the fact that some features are better conceived as objects and others as fields. As we mentioned there, this has implications for how we represent geographic information in the GIS. In the vector approach, reminiscent of object conceptualization, the precise location of each object, point, line, or area in a distribution is described. In the raster approach, reminiscent of the field conceptualization, the study area is divided into a set of small, usually square cells with the content of each cell described or quantified. The vector approach is more often suitable for human or cultural data, such as roads or cities, while the raster approach is more often suitable for natural geographic data, like elevations or rainfall. In either approach, a vast amount of different spatial information can be stored, accessed, compared, processed, analyzed, and displayed. A GIS database then can be envisioned as a set of discrete informational overlays, linked by reference to a basic locational grid of latitude and longitude, or some other coordinate system. The system then permits a separate display of the spatial information contained in the database. It allows the use to overlay maps of different themes, analyze the relations revealed, and compute spatial relationships. It shows aspects of spatial associations otherwise difficult to display on conventional maps, such as flows, interactions, and three-dimensional characteristics. In short, a GIS database, as a structured set of spatial information, has become a powerful tool for performing geographical analysis and synthesis. A GIS data set may contain a great amount of place-specific information collected and published by the U.S. Census Bureau, including population, distribution, race, ethnicity, income, housing, employment, industry, farming, and so on. It may also hold environmental information downloaded from satellite imagery or taken from geological survey maps and other governmental and private sources. In human geography, the vast and growing array of spatial data has encouraged the use of GIS to explore models of regional economic and social structure, to examine transportation systems and urban growth patterns, and to study patterns of voting behavior, disease incidence, accessibility of public services, and a vast array of other topics. GISs are an essential tool in the process of voter redistricting. For physical geographers, the analytic and modeling capacities of GIS are fundamental to the understanding of process and interrelations in the natural environment. Because of the growing importance of GIS in all manner of public and private spatial inquiries, demand in the job market is high and growing for those skilled in its techniques. Most university courses in GIS are taught in geography departments, and GIS and remote sensing is a primary occupational specialty for which many geography undergraduate and graduate majors seek preparation.